With nearly 2 billion kilometers deployed around the world, optical fiber is the backbone of today's most advanced telecommunications networks. Fiber is assembled into optical cables that link continents, cities, and neighborhoods around the world. This thin, flexible strand of ultra-pure glass is capable of carrying voice, data, and video information in the form of light signals at very high speeds. Let's take a closer look at this revolutionary transmission medium. Optical fiber is very thin. One strand is about the diameter of a human hair. It is comprised of two basic elements made of glass, the core and the cladding. The core, the center part of the fiber, is the area through which the light signals are transmitted. The cladding layer completely surrounds the core, keeping the light from escaping. There are two different types of fiber, single-mode and multi-mode. Single-mode fiber has a small core diameter designed to carry light in a single path over long distances. It has high information carrying capacity and low attenuation, and is the most widely deployed optical fiber in the world. Multi-mode fiber has a larger core, which allows light to travel down many paths simultaneously. Typically, multi-mode fiber is deployed in data centers, local area networks, and storage area networks, where it is more cost-effective than single-mode fiber. Corning invented the first low-loss fiber in 1970 and has continued to deliver significant performance improvements for the past 40 years through continuous innovation. Three key attributes that can limit the speed or information carrying capacity of the optical fiber are attenuation, dispersion, and bend-induced loss in the form of macrobending and microbending performance. Attenuation refers to signal loss along the length of the fiber. In this illustration, the light gets dimmer as it travels down the fiber. It can be caused by the quality of the glass itself or can be induced by bending. Dispersion is the distortion of a signal along the fiber length. This occurs because different spectral components of the optical signal in the optical fiber travel at different speeds. In this example, different wavelengths are represented by the red and yellow light. Macrobending and microbending are optical effects that occur when the fiber is bent from a straight axis. Microbending is an attenuation increase caused by high-frequency, small-radius bends along the length of the fiber. Macrobending is the attenuation associated with bending or wrapping the fiber. Both of these conditions can allow light to leak out of the fiber, meaning some of the original signal is lost. Using a bend-insensitive fiber like Corning ClearCurve single-mode or multi-mode fiber will greatly reduce the loss caused by macrobending. Optical fibers operate on the principle of total internal reflection, which keeps the light within the core and guides it down the length of the fiber. Refraction refers to the bending of light as it passes from one substance to another. The glass used in the fiber's core has a higher refractive index than the glass used in the cladding, so that the light can be trapped in the core by reflection at the cladding interface, as it propagates down the length of the fiber. Two additional characteristics of single-mode fiber that are important are cutoff wavelength and mode field diameter. Cutoff wavelength is the wavelength above which a fiber will support only a single mode. Wavelengths below the cutoff support two or more modes. The cutoff wavelength is determined by the fiber's refractive index profile, the length and bend of the fiber, as well as the cabling process and deployment conditions encountered during use. In a single-mode fiber, some of the optical power is actually guided outside the core. In fact, as much as 30% of the light propagates in the cladding layer of some fibers. The mode field diameter defines the size of the optical power distribution in the fiber. Multi-mode fiber has two important characteristics: numerical aperture and core size. Numerical aperture is the measure of the angular range of acceptance of light into a fiber. The angle over which a fiber accepts light depends on the refractive indices of the core and cladding glass. Core diameter is a fundamental design parameter of multi-mode optical fiber. The larger the core, the more modes of light can propagate through the fiber. Multi-mode fiber has a much larger core size than single-mode fiber. Optical fiber is strong, flexible, and reliable. Inch for inch, it's stronger than steel and more durable than copper. Fiber offers excellent signal performance over a wide range of environmental conditions. Since fiber carries light instead of electricity, it is unsusceptible to lightning strikes or electrical faults, and, unlike copper, it does not corrode or rust. As a result, fiber reduces maintenance costs and has a proven record of reliability in the field. In fact, it is common for customers to report to Corning that cables installed in the late 1970s or early 1980s are still in use today. Optical fiber is cost-effective, durable, and scalable, has low attenuation, and it features the superior transmission quality needed for high-speed transmission of voice, data, and video in today's leading applications. To learn more, visit our website or contact your Corning account representative.